You know, the next talk will be given by Professor Dongyan Xu from the Computer Science Department in the College of Science. And it really addresses a really important and critical point. You know, as technology evolves, we find sensors and computer networks everywhere that pervades everything that we do in life, in society. Questions of cybersecurity to our physical infrastructure become more and more important. And Dongyan is tackling this problem with his team, and he's going to tell us all about the progress that they have been making in cyber-physical vetting of critical infrastructures. So, Dongyan.
All right, so good afternoon. My name is Dongyan. I am a professor in the Computer Science Department, and I would like to talk to you about some of our recent advances in our efforts in addressing the security and reliability of cyber-physical infrastructures and systems. So this is really a team and multidisciplinary effort. I'm going to acknowledge my collaborators. Many of them are from College of Science and Engineering. I will acknowledge them at the end of the presentation. So the goal is actually very simple. We want to actually protect our critical cyber-physical systems and infrastructures that are increasingly computerized. So you actually see a lot of the physical systems being retrofitted or equipped with computers, microcontrollers, embedded systems to actually control the physical operation of these systems. And this is actually good and bad from a security researcher's perspective. We actually see a lot of challenges and opportunities, right? So you have been hearing stories about all these attacks. These are not the typical kind of a cyber attack. We're not really talking about computers being hacked. We're really talking about physical systems and infrastructures being disrupted and sometimes even destroyed by some kind of by some threats that come from the cyberspace, right? Starting from the notorious Stuxnet warrant that brought down a lot of the nuclear reactors in Iran back in 2010, and then to more recent incidents where hackers remotely manipulate a kind of a river dam in upstate New York from like 5,000 miles away. And more recently, actually just 2 years ago, where a whole bunch of CATV cameras got hacked, and then they all at the same time issue HTTP or DNS requests, bringing down actually 1/2 of the internet infrastructure of the United States. And you have also heard reports about, a drone being hijacked or being detoured because of some, GPS jamming and malware compromising the microcontrollers. So these are real stories, right? So the thing is that you are not just hearing these stories from movies and novels. Now they are actually happening in real world. So we feel that it is imperative to enhance the security of these cyber-physical systems in a more holistic fashion. We're not just looking at the physical aspect of these things, and we're not just looking at the computers. So this actually brings together a multidisciplinary team of researchers addressing different aspects of the challenge. So since the start of the project, we have been making a lot of progress both in research and outreach. Back in April 2018, we held the first workshop on cyber-physical security in affiliation with the Serious Security Symposium, and we were able to attract more than 110 attendees from government agencies, industry, and university. And we had 2 keynote presentations, one by Dr. Jonathan Smith from DARPA, the other one by Dr. Louis Shaw from the University of Illinois. So these are really the authorities in cyber-physical security, and we feel that this is actually a great event that brought together people and motivate researchers from different areas to address the common theme from different angles. So we will continue to host similar events in the future, and so we are actually planning something later this year. So quickly, this is actually the last slide that I copied from my big idea competition. So after that, everything will be new. So what the general approach we're taking is really to take a cyber-physical system or infrastructure and really map it to 2 different planes, the cyber plane and the physical plane. And we try to look at the interrelation or dependencies between them, and we try to actually look at some of the vulnerabilities that cross the border between cyber and physical. So the first thing is always to discover, because many of these systems are legacy systems, there may not be a kind of a operation manual or any kind of a documentation. You really have to find out, how these, components work together, right? So once you discover how the entire system works, because we're really talking about a system of multiple subcomponents or subsystems, and you will be able to have a better understanding, a more panorama view of the entire system. Then you will be able to do what we call the vetting. So you actually try to stress the different components of the system from different angles, and you want to actually expose the vulnerabilities, loopholes, and weaknesses. And then with that, you want to actually demonstrate in a very concrete way how exploits or attacks can happen by exploiting some of these vulnerabilities and the loopholes. So this is actually the third stage, which we call the prototyping. The challenge here is that, for many of the real-world cyber physical infrastructures and systems, you really cannot launch a real attack against them, right? So in this case, but at the same time, you want to show with realism these threats are new. So then you will have to strike the balance between real-world impact and realism of the attack, right? So this is actually the challenge that we're facing in demonstrating in a very concrete way how these vulnerabilities can be exploited to cause real damage. And finally, retrofitting is the step that actually fix or enhance an existing cyber physical system and infrastructure so that they can be immune from future attacks, exploiting the similar or same vulnerabilities that we have discovered earlier. So this really kind of create a kind of a workflow in enhancing the security and robustness of cyber physical system. So in the past year and a half, we've been looking at a bunch of very different cyber physical systems. So let me start with the story of the study of a commodity drone, right? This is the typical quad rotors control model. So as I said, we try to map the same system to the physical plane and then to the cyber plane. So this is what I call the control/physical plane, right? With multiple controllers, motors, sensors, and things like that. And ultimately, you will see that the controller will be implemented as a piece of control program, right? And then as a computer scientist, I realized that, I look at the program, and then I thought that, oh, this program is actually relatively well written. There are no, buffer overflow or all kinds of traditional bugs and vulnerabilities that you tend to find in computer programs. But then in the study of this system, we realized that at the interface between the control plane and the cyber plane, there are a new kind of bug that emerged. That is the kind of bug that you introduce when you inaccurately or incompletely implement the control model. In other words, the control model on the left is not accurately and fully reflected by your program. That actually leads to some vulnerabilities and loopholes that can be exploited by adversaries. So this is actually a kind of a quick demo of a bug that was actually triggered in a very malicious and stealthy way. So I will show you. So unfortunately, I do not have the real a demonstration with the real vehicle. So as you can imagine, this is really this can potentially be a very costly business because we actually broke quite a few drones because of crashes and things. So I will just show you the demo here. So the thing is that, this is a kind of a very simple flight path, right? Starting from waypoint 1 all the way to waypoint number 4. So in 1, we're supposed, it is supposed to cruise, right? And at a certain point, it will make a right turn flying towards waypoint number 4. So suddenly you see that the vehicle's operation gets very unstable. And it will remain so towards the end of the tour. So if you actually if you compromise the program in a slightly different way, you can crash it very easily. So I chose not to do that. So the thing is that this accident is actually very difficult to investigate because I'm not sure if you noticed, actually at the very beginning of the video, somebody actually modified in a very minor way, seemingly minor way, one of the control parameters. And by the way, this is totally legal, legitimate operation that operator can perform via the remote control. I just set a value, right? I mean, actually, it's there, the XY velocity p-value. And I set it, and after setting the value, the drone actually continued to operate normally for a sustained period of time. So when the accident actually happened, it is actually not easy to create or establish the causality between the crash and this parameter setting operation. So it took us a while to investigate this accident, and by doing this, we traced all the way from the FDR, the black box kind of a flight data records, right, all the way from the control logs to a specific bug in the program. So as it turns out, this control program, I'm not going to name the name, but it's a very popular one, actually failed to enforce a bound tracking logic that is mandated by the control program. It basically accepts whatever control parameter value that the user or this operator supplies. So that's kind of dangerous. Of course, we did ethical hacking. We actually reported this bug to that organization, and we waited until the patch is released. And so before that, we waited until then to actually publish the work. So that's one story. The second story is a completely different thing. This is actually a kind of a mock-up chemical plant, right? It's simulation, but the software that runs that executes to run those controllers are real. So this is what we call software in the loop. So the physical stuff is fake, but the control program is real. So what we do is that we look at the control program that control those valves, right? You see those valves that control the pathway between the reactor, the purge, and the container for the final product. So this is the program. So this actually looks very different from the traditional program that we look at, because this is what they call the PLC program, Programmable Logic Controller. It's highly visualized. It's kind of cool, right? But then there are also vulnerabilities or bugs in the program. And if you use the traditional quote-unquote computer science kind of a testing, you won't find it, because again, this bug is highly related to the model, the PID control, very simple, right? Control 101 kind of model that is not accurately reflected by this program. And then with this vulnerability, you are able to, so adversaries will be able to actually launch remotely an attack, maybe from the computer like this HMI, right? Human machine interface machine in a typical SCADA system. And you can remotely launch the attack. First contact this program, and then by providing an invalid parameter, the program causing the program to misbehave. So let me show you at least the visualized version of this attack. So the attack is launched remotely. You won't see anything, right? The adversary can actually sit in the control room. So let me do a little fast forwarding in the interest of time. So in this case, I deliberately block the valves, so the pressure gets piled up in the reactor. Did it work? Oh, here we go. Right? So the thing is that you can visualize that, the thing is that I maliciously completely shut down the valve that actually unleash the pressure coming out of the reactor. And this can be done remotely. And if the adversary cares about stealthiness, he or she can actually create a fake scenario, fake situation awareness in the control room. And the people sitting in the control room will not see anything, because you can easily reconstruct a kind of a fake scenario for that. So this one is what I call not smart building, but scary building, because the whole remote control can be easily hijacked and taken over by adversary. So all of a sudden the room becomes dark, because everything is controlled wirelessly through all these IoT gadgets with, again, vulnerabilities. And again, even worse, they can also fake situation awareness. So in the control room or in the building deputy's office, he or she look at the screen, everything is normal. But this is what really happens in the room. So by showing these, again, I like to demonstrate that the vulnerabilities exist widely, and you do need to actually follow that vetting illustration or demonstration and the retrofitting to actually fix the problem. So in the past 2 years since the Big Idea competition, we have received more than $11.5 million of external funding to actually look at different aspects of it. So I would like to highlight 2 of the projects that are ongoing. I actually just finished the site visit yesterday. So the first one is really about retrofitting autonomous vehicles. So we know that autonomous vehicle has a control model that has two aspects, right? The vehicle dynamics and the control algorithm. And again, the control algorithm or the control model gets reflected or implemented by the control program. So again, it follows the same workflow. Reverse engineering or discovery, vulnerability discovery, and then retrofitting the controller. While we do this, we also care about the real-time properties that actually control or govern the operation of the drone to make sure that no real-time deadlines are violated. And we again take that cross-layer approach, right? We saw that earlier, the control plane and physical plane and the interrelation between the two. So we follow the same methodology. We try to discover vulnerabilities not just in the control program, but also in the control model and even in the physical vehicle. Maybe the blade is not, is not very properly modeled or properly manufactured, or the shape doesn't, have a certain kind of a vulnerability, things like that. So we vet commodity as well as homemade drones and ground vehicles. And there are some very interesting, that's my timer telling me that my time is up. Okay, so let me speed up a little bit. So this one really shows the drone without protection, with the vulnerability being exploited. So this is the one after the retrofitting. Same drone, same control program with minimal, kind of like a minimal intrusive kind of a correction. So this is when, so now the attack is launched. You actually see nothing, but gradually, since the control program at this moment is corrupted, you can no longer trust it. I can only kind of fall back into this fail-safe operation by just landing it, right? At least the drone is not, did not crash. So that's that. I guess any talk has to have an AI element. This one is no exception. So this one actually shows you with a commodity drone. The commodity drone does not come with fault-tolerant control, robust control, no. But I can actually just do just like real-world flight school. I'm training the drone to fly. I give the drone all kinds of adversary condition, operation environments, contexts, and I give the drone a good reward if it responds to the adversary condition correctly. So just like how we train students, this is how we train the drone, right? So you have to run this, again, you cannot do this using real vehicle because you cannot afford crashing them most of the time. In fact, 99% of the time they will crash. But the key thing is to capture those good runs, right? Because the good runs represent good experience. And you want the student, quote unquote student, to remember the good experience, to actually apply that to real world, to real production flight. So this is really the thing. I have a commodity drone with a commodity control program. I only need to insert that little reinforcement learning policy module in a minimally intrusive way. And all of a sudden, this drone has AI, right? And you will see that. So now the attack is off, and you see maybe a little bit of the glitch, but now the reinforcement learning module actually used the lessons that it learned in the past to respond to this kind of anomalous situation, maintaining the normal operation of the vehicle. So the other project that I want to quickly touch on is this project that we vet not just individual system, but an entire IoT network, right? So we specifically target networks that are very close to the physical world, like IoT, SCADA, industrial control systems, and onboard vehicle network. So they share a set of common characteristics, and so this is how real we get. I spent some of the big idea money to purchase a retired vehicle from the transportation department, and this is how we instrument the vehicle to demonstrate that your current CAN bus system is actually fairly vulnerable. This is actually not new, right? Everyone knows that, but I want to actually come up with the advanced defense or retrofitting to actually mitigate the threat. The second testbed that we built is a IoT or building monitoring environment where we have all these little monitor to actually monitor the operation of IoT devices like your smart lock, your refrigerator, your sensors, to prevent adversary from adding a malicious imposter or a malicious or spoofing device, pretending that it is the real thing. So this will require some kind of a dynamic modeling of the physical and cyber characteristic of the IoT devices, so that we actually monitor this from 1, 2, and 3 vantage points. So at every time moment, you actually correlate the observations collected from these 3 vantage points. And by doing that, and also by using offline training and data analytics, you basically create a profile of what a good device is supposed to be. So any spoofing device will expose itself because the characteristic or the signature or the footprint will deviate from the signature that we obtained earlier. So this is actually a very simple demo where I use my laptop to fake a door sensor. And by the way, that is possible. I mean, I can actually get the same MAC address, the same protocol. It's the same. But again, based on our profiling-based detection, we are able to detect the spoofing of this fake door sensor in real time. And this is actually a visualization of how that detection happens, right? So the left portion of the chart shows the normal observation, right, by these 3 vantage points. And then as soon as the bad device starts to communicate, the pattern will change, and this will be caught in real time. So again, summarize, cyber physical security is really the frontier of security. And we follow this discovery, vetting, and retrofitting workflow. And there are a lot of multidisciplinary challenges and opportunities. So I do like to acknowledge my Big Idea team members as well as my other research collaborators. It is actually these people who make all these interesting stories happen. Thank you.
Thank you, Andy. All right, are you scared yet? I am. I'm glad you're on the team. So that's what I gotta say. I'm not on the other team. Questions for Dongyan? Yeah, Nate.
You mentioned towards the middle and towards the end about retrofitting some of your solutions onto existing technology. How far away do you think your team or maybe anyone at large is from, I guess, making those retrofitting solutions commercially available?
That's a great question. So actually, in our projects, we have a industry partner that will be responsible for transferring and independently assessing and re-establishing or re-implementing the technology to actually deploy them to folks or customers in the defense community. And so that is actually ongoing. So I'm very hopeful that the prototypes and technologies that we're developing here will, in the foreseeable future, be transferred somehow in some form, maybe in completely different form, to real-world demonstration. Yeah.
Great. Dongyan, along those lines, if I may, the Department of Commerce is asking sort of generally around the community in the United States for input on export control of advanced new technologies. Are you concerned about, is this something that might impede commercialization or might limit in some sense the activity?
I'm not. So the thing is that I think this, these research projects are set up in a very nice way. So we at the university, we are only looking at the basic or fundamental research aspect of the effort. And then the technology transfer or re-implementation will be delegated to our industry partner. Yeah. And I don't even know, and I don't want to know whom they will be dealing with. Okay. And that isolation will be established at that moment. Yeah.
Good. Yeah. Other, yes, Rosie?
Thank you very much. Your presentation was so interesting. This seems to be an area where technology is just way, way ahead of policy making. Exactly. And so if you had any advice to give to policymakers, what would you say?
I would just say that technology advances in such a fast pace. We will definitely like to actually understand so many technologies are being deployed without fully vetting or fully understanding the negative side of it, right? The negative impact or the consequences or some of the liability issues that arise following those. So this definitely calls for more study, more timely study per technology on a per technology basis, right? Autonomous vehicle or drone, we definitely need, to work very closely with policy researchers to actually better understand the non-technical, actually to understand the issues at the border between technology and policy. Yeah.
Let's get together, right?
Yeah, absolutely. Yep.
Yeah.
Yes.
So I'm curious, what would stop the retrofitting technology from being hacked? I mean,
That's a great point. In fact, that's why I mentioned this, right? I do have a response to that.
okay.
This needs to be done iteratively. So it's not a one-shot effort. Once the retrofitting is done, you need to constantly monitor new threats, and then you actually need to, every now and then you do actually need to redo the entire workflow to make sure that the system is always up to date, just like how we maintain, how we keep our software installation up to date, right, in our PC, laptop, and smartphones.
Okay.
Yeah, I mean, I'm advocating this. I'm advocating doing this to our cyber physical system or our physical infrastructure. Maybe your highway needs an upgrade, right? It needs a kind of a, this kind of a vetting or re-evaluation, or your building needs to be, updated.
Okay, that makes a lot of sense.
Downtime.
Yeah. Thank you.
Yep. Thank you.
Questions? Let me just ask you maybe a final question.
Sure.
I mean, there are IoT sensors being deployed in all kinds of environments right now.
Yeah.
How confident are you that these kinds of security measures are being introduced into the, let's say, public sector IoT sensors that are getting deployed? Darcy Bullock is not here today. He's the director, I don't think so. Let's see, no. So he's the director of the Joint Transportation Research Center, which is funded by the Indiana Department of Transportation. They're putting sensors on traffic lights that eventually will tell your car whether the traffic light is going to turn red or whether somebody's coming in the other direction, so you avoid a collision. How easy would it be to hack those sensors and make you crash, okay, right? So are you confident that, as these things get deployed, that these security issues are being taken into account and these vulnerabilities are being fixed?
I'm not. So that's why I'm advocating the vetting. So I think before any IoT technology is deployed in real-world operation, it has to go through this kind of a vetting process,
okay.
And it has to go
So
through
this
a
is what you're-
certification
yes.
process. So that's something that
So
I'm
that's the
advocating.
policy side of it too, right?
Yes.
Yeah.
Absolutely. I'm not. So.
Okay. Thank you, Donya.
Yep.
All right. Okay. So thank you very much. Fantastic.